Hello. This lecture will cover pages 15 through 17 of my lecture notes. Please print those pages out and have those pages in front of you as I present this lecture on Basic Concepts, Chapter 1C, Independent Sources and Dependent Sources. We're going to start out on page number 15, and we're going to talk about independent sources versus dependent sources. Independent voltage and current sources. This is the symbol for an independent voltage source, and this is the symbol for an independent current source. Now, if you take a look here at this independent voltage source, the voltage is constant, independent of the current in the rest of the circuit. So if this is 10 volts, or this is 100 volts, or this is 2 millivolts, the voltage between this terminal and this terminal of this voltage source is a constant, independent of the current that flows in the rest of the circuit. And a current source, the current is constant, independent of the voltage in the rest of the circuit. In other words, if this is 5 amps here, or this is 10 milliamps here, that tells you that there is a current flowing from this point to this point, and it's a constant current all the time, independent of the voltage anywhere else in the circuit that this is in. These are independent voltage and current sources. Now, we also have another symbol, the battery. If you remember the battery that had those parallel plates, that's another way of drawing an independent voltage source. But generally speaking, from this point on, this will be a typical independent voltage source, and this will be a typical independent current source. Next thing I want to talk about are dependent voltage and current sources. These are very important. There's two different types of dependent voltage sources, and there's two different types of dependent current sources. Now, these are so important that we mention them a couple more times in the course. Back on page 38, we're going to refer back to this page. And what it's going to say here on page 38 is look over page 15 in these lecture notes. These controlled sources are extremely important because in future EE courses, they are used to model physical devices such as the bipolar junction transistor, the field effect transistor, metal oxide semiconductor field effect transistors, the MOSFETs, and insulated gate field effect transistors. So you're going to see these in future courses, and the way that they model these types of active devices is with one of these four different types of dependent sources. Now, this is the way you draw dependent sources. They're not circles, they're diamonds, first of all. So when you see a diamond, you know it's a dependent source. Secondly, if you see a plus and a minus in the diamond, these are dependent voltage sources. So here's two different types of dependent voltage sources. And if you see a diamond with an arrow in them, just like the arrow up here, an arrow is a dependent current source. If you see a diamond with an arrow, it's a dependent current source. Let's take a look at the two different types of dependent voltage sources. This is a voltage controlled. This first one is a voltage controlled voltage source. Notice it's a voltage controlled and it's a voltage source. This is a current controlled voltage source. In other words, the voltage at this point, whatever this voltage is right here across this element here, it's dependent on another voltage or current somewhere else in the circuit. Well, in this case, it's dependent upon Vs, which is somewhere out here in the circuit somewhere. These are two different circuits here. So this Vs is somewhere out in the circuit. And depending upon the value of that Vs, this voltage source will take on a parameter. So the voltage at this voltage source is dependent on another voltage in the circuit, wherever Vs is defined. Over here, this is a current-controlled voltage source. It's a current-controlled voltage source. So what's the value of this voltage across this dependent voltage source? It depends upon Is, some current somewhere else in the circuit. On these current sources, this is a voltage-controlled current source, where the value of this current is dependent upon a voltage somewhere else in the circuit. And this is a current-controlled current source. So let's review here. When you see diamonds, they're dependent sources. When you see plus and minus signs, they're voltage sources, and when you see arrows, they're current sources. And then you have to look at how they're defined. This is clearly a voltage-controlled voltage source. This is a current-controlled voltage source. This is a voltage-controlled current source, and this is a current-controlled current source. They're very important. On page 16, I'm going to talk about example 5.1. A little difficult to see here, but basically there's two different problems here. We're going to look at problem A. This is a model, some type of device. Notice it's a voltage-controlled voltage source in figure A. A voltage-controlled voltage source. There's your dependent voltage source. Now, notice that it's depending, the parameter it's controlling parameter is Vs, and Vs is given out here in the other part of the circuit. So if Vs is 2 volts, what's the output going to be? Well, the output's going to be whatever this source voltage is here, which is 20 times Vs. That's 40 volts. V out is 40 volts, and you can see how they work that out up top here. Over here, this is another model. It shows current, and it gives you current out. So this is a current-controlled current source right here. What's the value? Well, it's 50 times Is, where Is is given as 1 milliamp. So if there's 1 milliamp in this part of the circuit, that means the value of this current source is 50 milliamps. So the answer is I out is equal to 50 milliamps out here. Now, I'm going to go a step farther, and I'm going to talk about voltage gain and current gain. They call it up here voltage amplifier, or they call it an amplification factor, and down here they call it a current gain. But I defined a few things out in here, and I'm going to look at these in a little bit more detail. First of all, you might want to stop the video and look this over once I describe it. But this box right here is going to represent this device right here. It's going to represent this device as an unknown device. And I have some Vs on the input, and I have some V out on the output. Well, it turns out in this example, Vs is 2 volts, and V out is 40 volts. So we're going to find something called a voltage gain. A voltage gain is equal to A sub V. That's the symbol for a voltage gain in this course. And it's defined by V out over Vs, the source voltage. A lot of other textbooks define it as V out over V in. So the voltage gain is what you get out divided by what you put in. It's a gain factor. So the voltage gain for this example is equal to 40, that's 40 volts, over 2 volts. The volts cancel, and the voltage gain is 20. It's not 20 volts. The units cancel. The voltage gain is 20, which means it's a multiplication factor. So the voltage gain of this amplifier is 20. So if you put in 2 volts, you get out 40 volts. If you put in 3 volts, you're going to get out 60 volts. If you put in 4 volts, you're going to get out 80 volts. It turns out we like to show voltage gain in terms of dB, which we'll talk about later. Here's the equation for that. Voltage gain in dB is 20 times the log of the absolute value of the voltage gain, because you can't take the log of a negative number. And you're going to say, well, how can you end up with a voltage gain being negative? Well, sometimes you're going to find out in about 2 chapters that you might put 2 volts in and get minus 40 volts out. You might put minus 5 volts in and get plus 25 volts out. There can be a 180 degree phase shift between the input signal and the output signal. That's all that's telling you. Well, if you form the ratio, you're going to get a negative value, and you can't take the log of a negative value. So we're going to take the absolute value of the voltage gain. You take 20 times the log of the absolute value of the voltage gain, you're going to get the gain in dB. In this case, I plugged it into my calculator. I get the voltage gain in dB is 26.02 dB. That's the units, dB. There's the voltage gain in terms of a ratio. Here's the voltage gain in terms of dB. Engineers know that that is the same thing as that. It's just a different way of looking at it. One's in dB and one's a ratio. It's a multiplication factor, though. Don't forget. If you put 2 of these back to back, and one has a gain of 20 and one has a gain of 5, you don't get a gain of 25. You get a gain of 100. It's multiplication. This is multiplication factor here. And then I want to take a look at the second circuit. this circuit right here, which was the current gain. Look it over. We had 1 milliamp coming in. We got 50 milliamps coming out. So if I model that right there, it looks like this. Again, you can stop the video after I discuss this and look it over. This is called the current gain. The current at the source, the current on the output. The current gain, A sub I, not A sub V, it's A sub I, is defined by I out over IS. Some textbooks, it's I out over I in. The source input current and the input current, same thing. The voltage gain, the current gain is 50. That's 50 milliamps out and 1 milliamp in. You get a current gain of 50. That's not 50 milliamps. These 50 milliamps cancel. That's a current gain of 50. It's a multiplication factor. So you have a gain of 50 here. You put in 2 milliamps here, you're going to get 100 milliamps out here. It's just a multiplication. And in dB, same thing. The current gain in dB is 20 times log of the absolute value of the current gain. In this case, it's 33.98 dB. On the exam and on the quizzes, you're going to have to give me current gain and voltage gain as a ratio and current gain and voltage gain as dB. Then I'd like you to take a look on page number 16. There's a learning assessment. Determine the power supplied by the dependent sources, A and B. Look this over and make sure you can do it. The power supplied in figure A is 80 watts, and the power supplied figure B to the device 1 is 160 watts. And then example 6.1, calculate the power absorbed by each element of the network in this figure. Also verify that Telegin's theorem is satisfied by the network. That's the conservation of power, that Telegin's theorem. We're not going to talk much about it, but basically it says that the sum of the powers supplied in this circuit have to be the sum of the powers absorbed. They have to be equal to one another. So you just go through this circuit and they calculate the power absorbed by each element using the sign convention for power. Remember, I'm not concerned about the sign convention for power as negative current. They have current defined. Current gone into the negative node of a terminal is negative current. We don't do it that way. We just calculate, we just take a look at each direction of current. You might have to look in the textbook to see this, because it's very, very difficult to point out where these arrows are here and here and here. But you know, if you take a look at these, this right here is clearly going to, the current is going, it looks like, in that direction, so it's coming into the positive terminal. That has to absorb. Down here the current's coming into the positive terminal, it absorbed. Up here the current is flowing in this direction. That means it has to be coming in here on this part of that. This is a series part of the circuit. It's going into the positive direction, positive terminal, it's absorbing. Down here current, this 3 amps is coming up, going into the negative, so that's supplying power. Over here the current's coming down, it looks like, which means it's coming down up here. It goes into the positive terminal. In that case right there, it has to be absorbing power. So you go through that example 1.6 and make sure you understand that. And then example 1.7 in the textbook, I want you to look that over just so you can do the homework here. It's this problem right here, 1.7, a little difficult to see, but use Telegin's theorem to find the current I/O in this network here. Basically, they're just, this has to be a power that's, if you calculate the power in the power in the 2 amp source, that's this one up here, that's just right here. The power in the 2 amp source is up here, and the direction of current, the current is coming into the negative node, so that has to be supplying power to the circuit. So what I would do, I wouldn't use a negative sign convention, I would just put an S there. I'd say that power is being supplied. Down here at P2, Let's see where P2 is. That's right here. Look at the direction of current gone into that 2. This device. That has to be supplied as well. It's negative the way they calculate it. And you can go through each one of these, and down here the conservation of power. And then your unknown is I/O, and you can see if to hold the conservation of power in this network, I/O had to be 1 ampere. Had to be, according to this. These learning assessments are always valuable to look them over before you do the homework. On page number 17, you have the homework assignment number 1. I give you the answers, and then some of these I have worked out and posted in Canvas. That concludes Chapter 1.